Hello everyone, my name is Tomasz Masternak. I'm an engineer at Particular Software, where I deal with creating, design and implementation of distributed systems. So what I wanted to talk about today are forgotten lessons in distributed systems. And the first question that might come up to your mind is, I'm on the Way Forward conference. Why the heck should I learn about forgotten lessons? It seems to have something to do with the history. Why does it matter? So I think that it was the Isaac Newton who put it in proper words, and he said that if I can see further than anyone else, it's because I'm standing on the shoulders of giants. And I think that it's very true. If we want to make a proper progress in any area of interest, we have to look backwards at what has been already completed by different people who worked in that area. So this is why I've chosen forgotten lessons in distributed systems. So let's go on with it. But before I will delve into technical details or technical stuff, I wanted to tell you the story of Enki. So you might be surprised by Enki is not a distributed systems engineer. Enki is not an engineer. In fact, Enki is not even a human. Enki is actually an octopus, and to be honest, a pretty ordinary one. However, it did get its 5 minutes of fame about 2 years ago when the New York Times posted an article about Enki. And the name of the article was The Great Escape. So what happened was more or less this. Enki would spend the whole of its life in an aquarium tank in one of the zoos in New Zealand. One day, a member of the zoo entered the room when Enki was supposed to be, but basically Enki disappeared. So what this guy did is he looked at the surveillance camera recording, and what he realized is that Enki performed a pretty neat escape. So what happened was that the Enki went out of the aquarium tank, went on the floor, then traveled throughout the floor of the room and found the entrance to the sewer. Then it unscrewed the opening of the sewer and went inside to the piping system. There, it traveled around 200 meters until it found the pipe that goes into the ocean. And it was the last time that Enki actually resided in the zoo. It disappeared. Nobody knew what happened to Enki afterwards. So that article got me thinking. And my thinking was along the lines. It seems that those octopuses are really intelligent. So I did my bit of research, and what I learned is that in fact they are. And there is an argument between biologists to what extent, what is the extent of their intelligence. But some even say that their mental and neural capabilities are comparable to this, to what we have as humans. Now, the second thought that I had at that time was, okay, so if they are so intelligent, why haven't I ever heard about octopuses being super intelligent? You hear about dolphins, you hear about ravens, maybe about dogs, but not about the octopuses. And one of the reasons might be because they live deep inside the ocean and you do not meet them, but that wouldn't be a great ending of my story. So I will give you a different argument. And the argument goes along these lines. It's because the way in which they live their lives. And they live a pretty solitary lives. They do not meet any other octopuses, and apart from the moment in which they breed. So the female and the male meets, they breed, then the female will lay eggs and it dies afterwards. And the new generation of the octopuses is born. Now, you might be thinking, what's the analogy with computer science or distributed systems domain? And I think that the analogy is pretty big. And the reason is that sometimes I have a feeling that in the area of distributed systems and computer science in general, we copy the way in which the octopuses develop. Basically, after each generation, we reset the knowledge that we have in the industry, and this actually prevents us from making a true progress. So obviously, I am not the first person who noticed that, and there are a lot of arguments about what is the reason for such situation. So I mentioned a bit of those on my slides, and some of them go along the lines, the average experience of the developer or the engineer is pretty short, because usually their career lasts for 4 years or 5 years, and then they switch the area of interest. So it's a bit too short period of time to actually aggregate the knowledge and share it in a proper way. The other argument says the industry is driven by marketing, and we are following the trends and not the facts and the experience that we gather or gathered throughout the years. Some say there is a vast body of knowledge, and it's actually hard to find the information which is interesting, because distributed systems is a research area of at least 4 decades of history. Finally, some people say it's about unknown unknowns. When you enter the area, you just don't know what you should know because nobody else told you. And I think that the last argument is pretty much something that is my personal belief. In 2013, there was a pretty interesting blog post being published, which was titled "Notes about Distributed Systems for Young Bloods." And what the author was saying was that although we have a lot of knowledge, the access to the knowledge is probably the best that we ever had in the whole history of human race, and that applies to distributed systems as well. However, what we are lacking is hands-on practical advices that should be shared inside the industry. So a lot of people learn about distributed systems. A lot of people even read the papers that were very influential at the time that they were published. However, it's pretty hard to translate the theory to practice because the context changes. And if you do not have the proper experience, then it's a bit hard to actually apply the knowledge that you gain. So what I decided to do in this presentation is to share the lessons that I learned throughout my experience in a hard way, to make your life a bit easier, hopefully. And the other thing that I wanted to share with you is a bit of a historical perspective. So I want to show you that the things that I learned, let's say 5 years ago, were actually known for decades. However, for some reason, I had to learn them the hard way, and hopefully it will be a bit easier for you. So let's start with the first one. So the first lesson that I wanted to share with you goes like this. Local and distributed computing need different programming abstractions. So what do I mean about that? What I mean about that is if you are developing non-trivial systems, at some point you start to deal with distributed one. The reasons why you are put in this position might vary. So for instance, you might decide upfront that you want to go with the service-oriented architecture, or you want to go with the microservices. Or for instance, at some point, you decide to integrate with third party or with other teams that build other software in your company. And then one of the first questions that you need to answer yourself when you are a software developer is, okay, so how do I go about implementing a remote communication between different remote processes that combine my distributed system? And a very chosen solution is something that falls under the umbrella term of remote procedure call. But in concept, it's very simple. So basically what it says is that the local invocation of any given operation and the remote one should be indistinguishable at the level of code. So to give you a very trivial example of what that might mean is the piece of code that I included on the slide. So it does two things. First, it creates an order and then it requests preparation for shipment. Now, when you look at that code, it's not obvious whether those are two separate submodules which are hosted in the same process, or whether those are two processes that will communicate between each other and that I actually have to perform a remote communication to perform line 1 or line 2. So putting that on a graph, it might be one or the second situation. Looking at the code, you have no idea what is happening. So the historical context is this. The idea has been around for quite some time. Actually, the first written description of remote procedure call that I'm aware of has been published in 1974 in RFC 674. Sorry, I don't remember those numbers. And the idea was pretty much the same as I described it. The author stated, to make the development of distributed systems easier, we should provide a technology that would hide all of the complexity of distributed invocation and communication, so that people would write the programs just as if they were running in a single process. Now, even more interestingly, a year after that, an RFC 684 was published. And what the authors were stating is that the ignorance comes at a price. That even though it sounds very, very compelling to have such a programming model, what it actually does, it hides the problem, which prevents us from properly solving it. So if you look at RFC 684, you will find a bunch of arguments that are around, all around the realization that distributed systems should be written in a different way, because the inherent characteristic of the distributed system is that they fail. And they fail in a different way than the local computation. That you can have a partial failure, and the dependency between the parts of your distributed systems should be explicitly expressed in the source code. So what could be the alternative? After some time, I learned that there is something which is called the message-based communication. And basically, the approach that, that message-based communication is about is that you should express the remote communication in an explicit way in your source code. So this trivial example that I showed you previously would change a bit. So the first line stays the same, but in the second line, what I'm saying is that there is actually a message that travels from my process to some other process, which might be remote, and it's not the local invocation. So the question is, why should I actually care? Well, you should care because the communication comes at a price. So you might think about the size of the messages that you are exchanging, or the frequency at which you are exchanging the messages. What's more, you can have you can prepare your system for failures and just disable some of the functions of your system because you can easily identify them in code. So the example that I showed you changes in such a way that it's pretty easy for me to figure out whether I'm dealing with the first situation, that everything is local, or whether it's actually something remote which is going on between at least two processes. Now, message-based communication gives me even more, because if you think about it, the explicit modeling of communication gives me ability to actually provide different scenarios of message exchanges or different types of message exchanges. With remote procedure calls, what happens is that I do request, I wait for response, and I do it in a synchronous way. At least this is what most of the technologies that fall under that umbrella do. With message-based communication, you can go a step forward. You can have fire and forget communication. You can have publish, subscribe communication model. You can have scatter, gather, and even more complicated, customly designed for your purpose. What is even more interesting is that when you stop treating the communication as a magic black box and you start thinking about the messages, you can think about the channel that the message travels as an infrastructure that can give you guarantees. And those guarantees might be, for instance, persistence. So you might be able to send a message that will be persisted and delivered to the other process, even if it's not available right now, but will become available after some time. Not necessarily now, but eventually. The other thing that could be useful is, for instance, routing. So message-based communication makes things harder, but at the same time gives you a lot more flexibility that you can use in your applications and in the systems that you're building. Now, I want you to get me right. What I'm saying is not that remote procedure call is bad and that message-based communication is right. Because nothing in the engineering field is good or bad. We cannot say that something is good or bad. We can only say that something fits or does not fit a given purpose. So the lesson that I want to share with you is that if you want to go with the remote procedure call approach, because you identified the requirements and that's the best thing that you can think of, just go with it. But what I encourage you to do is have a look at the arguments that people put forward that are potential disadvantages of this approach. Okay, so that was the lesson number 1. The lesson number 2 is guarantees live at the business level. And what do I mean about that? If you look at the field of distributed systems, you very often hear about the infrastructure. And the infrastructure can be a messaging infrastructure, a storage infrastructure, but basically something that you build your system on top of. And in the context of that infrastructure, you can hear a lot of different adjectives. And those are something like reliable, ordered, secure, deduplicated, FIFO, a lot of adjectives. But a very interesting thing that has been noted already in 1984 in a paper called End-to-End Argument is that that thing does not directly translate to your business needs. So if you are writing an application, it is actually essential for you to figure out whether the guarantees that the infrastructure give you are enough for your business needs. And the argument from the authors was that usually it's not the case, that you can actually have to implement some custom logic on top of the guarantees that the infrastructure gives you to have a meaningful guarantees at the business level. Now, one of the interesting arguments that they give for such a situation is this. What they say, it's all about the economics. If you are building a solution and you expect that the problems at your business level will be solved at the infrastructural level, it would mean that that infrastructure has to be very specialized. And if that would be the case, it would be very expensive to build it because probably you would be the only consumer of that infrastructure. So just to get my point across, let me give you 2 examples. So the first one is the duplication of messages. Let's assume that you are building a pretty trivial application. You have something which is running in the browser and the other part which is in the backend. And in the browser, the user is able to place an order. So basically, there is a form, the user will fill it in, and they can click place an order. And one of the requirements from the business is we should do anything that we can to prevent the duplicated order coming from the client. So we want to make sure that by accident, the user will not place the order twice. Now, when you look at the infrastructure on which the internet works, you can identify TCP. And if you look at the specification, it says, okay, it's reliable, it can work under the SSL, so it can be secure. But also in the specification, there is a mention about the deduplication. So the way in which the TCP works is that the sender will send chunks of data to the receiver, but each chunk will be labeled with a sequence number. And if the receiver saw the sequence number that it received, it will discard it. So you can look at that and say, okay, is it the duplication? Problem solved. But then when you think about the requirement at the business level, you realize that that capability has to be built into your system and applied to ends of the communication that happens in your system. So the one end here is the browser and the code in JavaScript that is running there. And on the other hand, some business component which runs in the backend. And one of the solutions would be probably pretty similar to what the TCP is doing. Basically, coming up with some ID and storing the IDs that have been processed at the order's end and making sure that we do not get any duplicates. So that's example number 1. Example number 2 is, let's say that I want to share files and make sure that nobody tampered their content. And let's say that I am talking about some service which stores my data and it's available through SSL. One more time, I might be tempted to reason about that in this way. Okay, I'm communicating over SSL. It's secure, it's secured, problem solved. But then if you think about it deep enough one more time, you might ask questions, okay, but what's the storage on which my file will land? Is it encrypted as well? Who is the administrator of that? Is it possible that he will tamper the content of my file? And if you start asking those questions, it appears that in this given situation, the security guarantee that gives us the infrastructure that we use for solving the problem is not enough. That we need to build some additional functionality at the business level. And in this particular case, what we could do is say, okay, I'm providing the certificates for my users, and I'm uploading not only the file, but also the digital signature of that file. And then, even if the infrastructure is not super secured, the receiver, the other end of the communication, can actually validate the content against the signature that I included with my file. Okay, lesson number 3. There is no absolute time. What do I mean about that? In 1978, there was a paper published by Mr. Leslie Lamport, and I just want to mention him for a brief second because he's a person, if there is a single person that you should know about in distributed systems, it's him. He discovered or invented a lot in distributed systems, and if you start learning about internals of distributed systems and some fundamental theory around them, you will just come across Leslie Lamport almost all the time. So in the paper that I mentioned here, what he says are 2 important things. The first one is that when you start thinking about distributed systems, you should drop the notion of global time. So you cannot assume that all the processes that run in your distributed systems have access to a single source of truth in terms of clocks. So that will just not happen. That's it. You have to live with that realization. The second thing or insight that he had, which is pretty interesting, is following. What he says is that when we talk about time in different scenarios, what we actually use it for is not the absolute value. So if I say that something happened at 3:05 and the other thing happened at 3:07, it's not that important whether it was 3:05 or 4:59, but what's important is that the possible causal relationship between those events. So what he says is that we do not need the global time to actually track the causal relationships between the events that happen in our system. And what he says is that sometimes we can decouple time and the messaging, and that we can have a behavior that appears like a system which is synchronized in terms of absolute time, where in fact it's actually not based on any clock synchronization whatsoever. So let me give you one example of that. Let's say that you are building a system which consists of a big video wall. It's big enough so that there is no single computer that can actually render on all the partial screens. So it's actually divided into segments, let's say 4, and you have 4 different computers or 3 that are responsible for rendering parts of the wall. Now, for the person who looks at the wall, it has to be synchronized. Like every computer has to be at the same frame at the same time to make sure that you have a consistent view of what is happening in the whole screen. So one of the approaches that you might take is say, okay, I need a perfect time synchronization, which will be exactly the same as the wall time. But the problem is that that's hard. You can actually go with time synchronization, but you will have problems with initial synchronization, with hardware problems, with potential lag that you need to control. So you can actually solve this problem in an easier way, assuming that it's very unlikely that something will happen on the communication media, channel between your computers. One of them can play a role of synchronizer. And the only thing that it says, it sends those messages saying, now play frame number X, now X1, X2, X3, X4. And what happens is that for someone who is looking at the wall, it seems that the whole thing is synchronized, super synchronized, where in fact, those computers can have vastly different time measurements in their local system. Okay, my last example. This example goes, or I prepared this example to show you that there is a possibility that you will have a perfect time synchronization, but still it's not good enough to actually provide a causal relationship because we cannot always depend on the communication media that we are using. So let's assume that we have a chat application and it's peer-to-peer, so there is no single server. Every user of the chat has its own application. And there are 2 people who are talking with each other. It's Bob, Eve, and Alice. And what they want to do is they want to agree on the appointment time. And Bob starts first. So what he's doing is that he sends a message to Alice and Eve saying, let's meet on Monday. However, for some reason, the message to the Alice is delayed, but it gets to Eve pretty quickly. Eve sees the message, okay, Bob is proposing to meet on Monday. Actually, I cannot do it. So she types in, I cannot do Monday, let's meet on Thursday. Or I cannot do Monday, let's meet one day after that. And she sends out the message to Bob and Alice. Now, Alice gets a message from Eve before the message from Bob arrived. And she reads a message which doesn't make sense without the context, because she did not get the message from Bob. So you can see that even though those three different people might be very precisely synchronized in terms of time, this time synchronization is not enough to preserve the causal relationships between the events, because you need something more. Okay, that was my last example. If you have any questions, feel free to reach me out in the speakers area or whenever you find me. I hope that the lessons that I learned will be useful for you. What I encourage you to do is start digging into the distributed systems, because I think that they are very, very interesting. And right now we are, in my opinion, entering the era or the time in IT where everyone is a developer of distributed systems. So it's actually worth to invest some time into looking into that, those informations. Okay, thank you very much.